Sorbic alcohol and maleic anhydride react to give a bicyclic product. This is a Diels alder followed by intramolecular acyl substitution reaction. The structure of one of the isomers of the product is shown here. The product has 10 non-equivalent protons. At the bottom of the structure is the COSY NMR. As you can see, the NMR looks too complex for students and professors alike. On the right of the COSY NMR is a clear representation of it. The chemical shift values for each of the 10 protons are shown on the x and y axes and are also represented on the diagonal line with yellow blocks. The most informative peaks shown on the left are the cross peaks. These tell us which protons are coupled with each other. For example, the proton at 1.10 ppm couples or correlates with the proton at 2.60. The proton at 2.10 does not couple with any other proton. The proton at 2.60 couples to two protons, one at 3.10 and another at 5.80. Using these cross peaks, we can identify each proton in the molecule. First, identify the simplest proton. In this case, it is the methyl peak here. This methyl peak is the most upfield and shows as a doublet. Let us now see what proton the methyl peak couples with. A cross peak is shown at 2.60. From this, we can conclude that the peak at 2.60 must belong to the neighboring methine proton here. So far, we have identified two types of protons, the methyl peak using its chemical shift, and the methine peak using its correlation with the methyl peak. We will then use this methine peak at 2.60 to find out what other proton or protons it couples with. The cross peaks show that not only does it couple with the 1.10 peak, but it also couples with two other protons at 3.10 and 5.80. To identify which of the neighboring protons belong to 3.10 and which to 5.80, we can use the knowledge that alkene protons usually appear between 4 to 6. Therefore, the peak at 5.80 must be the neighboring alkene proton shown here, and the one at 3.10 must be the methine proton shown to the right. We can now choose the methine proton at 3.10 or the alkene proton at 5.80 to see if there is further correlation. Let us pick the one at 3.10. In addition to coupling to the one at 2.60, it also couples with the one at 3.40. The nearest proton with a 3-bond coupling that could couple with it must be the proton shown here. Therefore, we identify this proton to have a chemical shift of 3.40 ppm. Now let us concentrate on the peak at 3.40. We already see that it couples with the one at 3.10, but it also couples with the one at 3.20. Therefore, the peak at 3.20 is identified as the one shown here. Now let us concentrate on the peak at 3.20. We have already seen that it couples with the proton at 3.40, but it also couples with 4.10, 4.40, and 5.6. The 5.6 proton must be the alkene proton here, and 4.10 and 4.40 must be the methylene protons next to the oxygen. Further study is needed to distinguish between the two methylene protons. The coupling constants for each are shown here. The last proton that is not identified is the carboxylic acid proton. Carboxylic acids usually show around 12 to 13 ppm, and they are exchangeable. However, in this spectra, no peak in that range appears. Therefore, we might conclude that the singlet at 2.1 belongs to the carboxylic acid. This would be an unusual assignment and can be proven or disproven by carrying out D2O exchange experiment.